Let's start then. Uh, Last lecture I was talking about a little bit of background to digital circuit design. And in this particular discussion, what I'll do is take you through the steps involved in design of a very simple combinational circuit, combinational circuit IC. So, all right, before that, when we're talking about design, design is something that we're all the time engaged in our daily lives. And a little bit about design one can appreciate by taking a very simple example. Before I delve into combinational circuits, let's look at a very simple example of a design. So you want to go from point A to point B, right? And you have to design a travel plan. Travel plan from point A to point B. With, of course, every design comes with constraints. And the constraints in this case are you want to undertake the journey in less than whatever amount of time. Money is always a constraint. And so these are quantitative constraints. You can put numbers on them. Time is 2 hours or 3 hours. Money you can put, well, A could be your hostel, hall 3. B could be station, let's say. And you can put the time constraints, maybe 2 hours or 3 hours. Money you can put 200 rupees or whatever you want. And so there are quantitative constraints. And there are subjective constraints also, things that you cannot put a number. Comfort, for example, right? So it's difficult to put what number on this. So there are subjective constraints as well. In every design, you'll find that. Okay? So you want to undertake that. So how do you come up with a travel plan? Many times, a very simple approach would be generate a tentative travel plan TP1. Evaluate the solution against the constraints. So you come up with whatever you want to do, take a bus, take a tempo or whatever. Evaluate the solution against the constraints. If constraints are met, if they're met, they're fine. If they're not met, then of course you have to generate another solution either by, if it's a multi-leg journey, you may want to modify one leg of the journey. So you modify the existing one or you find a completely new one. Right? You may arrive at a solution, but there's a problem with this particular approach. You select one, and what if it satisfies your constraints? It's less than, it satisfies the time constraint, it satisfies the money constraint, it's less than whatever value we're talking about. And so it's a satisfactory solution, but you realize it's not the optimum solution. You just happen to pick one solution, and it's satisfying the constraints, but it's not an optimum solution. You could find another solution which may cost you less, may provide you with more comfort. So this is not a satisfactory solution. Just come up with one and see whether it satisfies the constraints and then be happy with it. A better one would be to generate a set of travel plans. TP1, TP2, TP3, a wide variety of travel plans. And the more the travel plans that you can generate, the better it is. So a large variety of alternatives you generate. And once you generate, well, then you search. Then you evaluate each one of them. You evaluate TP1 against the cost and the time and all that, TP2, TP3 and all that. And then on that basis, decide which is the best one. Right? So you've generated a set of possibilities and then you evaluate the possibilities and then decide. And so there's a greater chance that you'll find a more optimum one rather than the first thing that comes to your mind, apply it and see whether it works or not. Okay, so that's a better way of designing. Now, note that if you are looking for an optimum solution, what I'm trying to point out is you have to generate a set of alternatives. And how do you generate these alternatives? Well, that you will realize that experience will play a role. If you already know how to undertake a journey from point A to point B, from here to the station, if you already have some experience, you can generate more possibilities. Somebody who's totally new to the campus may not be aware of all the possibilities that are there, right? So experience plays a role in the design process itself, the kind of possibilities that you can generate. The other one is the imagination. Even if, let's say you have experience, you can always conceive of new possibilities. So imagination, creativity, all these are important parts of the design process. So somebody who has a lot of experience may generate TP1, TP3, and TPN and all that. may fail to generate TP2. Somebody who's more creative, more imaginative may generate a new possibility. So these play a very important role. Experience, imagination, creativity, these are all very, very important. They're not so important in analysis, but in design, these are central. Now, again, because both experience and imagination that you see are subjective, they vary from person to person. And therefore, the kind of outcome that you may generate, it depends on the person who's carrying out the design. So these are subjective things. Experience is subjective. Different people will have different experiences. Different people have different imagination abilities and creative abilities. So the solution that one may get is often not unique. You give the same problem to one person, he or she will come up with one solution, a design solution. You give it to another person, he or she may come up with another solution. That's quite common. On the other hand, analysis problems are usually, you give an analysis problems and you give a set of information and you're asking some new information to be deduced. Often the answers are the same. When you analyze, you come to similar answers as compared to design one here. So what you realize is that when I'm carrying out design, if I look at this simple process here, experience and imagination, of course, important, your ability to generate, evaluate, and modify alternative solution is key to achieving an optimum solution. There's always a time constraint. So if you can rapidly generate new alternatives, evaluate them, and if you're not happy with them, modify them. If that ability increases, ability to generate, evaluate, modify alternative solutions, you're more likely to arrive at a more optimum solution plan. All right, so these are, although I'm talking in terms of travel plans, these are central to all design. Your ability to generate. So anything that improves your ability to generate an alternative, evaluate, does it meet my time, money, and all those constraints? And then if I can rapidly modify. Okay. So you'll see that one of the tools of obviously that helps us to evaluate, helps us to generate, and all that is a computer. And so CAD tools, computer-aided design tools, are central to the design process. They allow us to evaluate, they allow us to modify. You can't think of any design right now without use of CAD tools. Okay, so they help us in this particular process here. The other part is, so experience, imagination, all of that you see here through this simple example. The other one is, suppose I make the journey a little bit more complex. So instead of traveling from, let's say, as I said, from your hostel to the station, if you have to travel from your hostel to, say, hostel in IIT Delhi. Right? So a different hostel in this thing here. So now, two things happen. As design becomes more complex, generally your ability to generate and evaluate alternative solution degrades. Because remember, the time is limited. So to generate a solution, because it's complex, it has many, many legs of journey here. So it will take you a certain amount of time and effort to generate a solution. And then you'll have to add up, you'll have to figure out the costs and time and all of that, add them up and come up with, is the design good or not? So all this degrades. And also remember, if there are 10 legs of journey, and each leg of the journey has 3 possibilities, so the number of possible options, they rise exponentially. So again, remember what we said was our design processes, optimum design processes, generate a set of alternatives and try to find the optimum one. So your search space becomes very large because the number of possibilities are huge. And so as the design becomes complex, arriving at an optimum design becomes difficult. So one of the techniques that people do is decompose the problem, hierarchical decomposition. In the sense that, the previous problem was travel within a city from point A to point B. Now I'm talking about travel between 2 cities. Right? So we won't handle this problem in the same way that we handle the previous problem. This is a more complex problem. So I may want to break my problem, decompose my problem into 2 parts. First, I'll try and figure out the travel between the city, between Delhi and Kanpur. And once I do that, once I solve this particular design step, then I'll figure out travel within the city. So my design now becomes a 2-step process. And you will realize that as I add more complexity to my design, what I may want to do is add a 3rd layer on top. So it may become a 3-layer design process here. So as the complexity increases, complexity of the design increases, the number of design steps, they also increase. And this is a hierarchical decomposition, is a technique that we commonly use to manage complexity here. And so more design levels are required here. All right. So with this background, I just wanted to highlight, some of the features of a design process. Let me come to a combinational IC design. I'm not talking about a circuit design. I'm talking about integrated circuit design here. All right. So I've taken a very, very simple example. Let's say, arbitrary example. Let's say you want to design an IC, which has 3 inputs, A, B, C, and 1 output, Y. And the relationship between the output and the input is this logical expression here. All right, so this is the design that you want to carry out. So you want to make an IC. All right, you want to make an IC. So IC would have 3 inputs, 1 output, 4 pins, input-output pins, plus it will have a VDD pin and a ground pin. Right, so 4 plus 5, 6 pin IC. Right, very simple IC you want to design, and it should have this kind of a functional relationship. Okay. Now, it's not just the function that you want to obtain. You want to obtain a certain performance. So let's say it's given that after you apply the inputs ABC, the output should become available within the time which is less than a certain value here. So there's usually a performance part here. Normally, also it would be given that your IC should not consume power above a certain value. All right, so I'm not talking about power at right now. So delay is usually given, and the other constraint is that your IC should occupy the minimum area. We saw in the last lecture, as the area increases, the number of ICs that you get, the yield and all that, they depend on the area. So that's always, even without saying it, it's always one of our goals that minimize the area of the IC here, minimize the area of the chip that will be required to implement this particular function. All right, so this is a very simple design. And so this is what I was talking about. You want to minimize the area to minimize the die cost here. All right, so this is where I want to be. My whole design would be complete if I take this logical expression and, as we said in the last lecture, translate it into a layout. A layout with all the transistors that are there in it and all the interconnects and everything. It shows a plan for manufacturing an IC which will perform this particular function here. This, of course, this particular chip with all the design here would, as I said, placed in a package and interconnected with pins so that you'll have the final IC. So, first decision you'll have to take is, are you going to do a full custom design or a semi-custom design? Full custom design meaning design from scratch, which means each transistors, each gate, everything is designed in accordance with your problem in hand. That's what is meant by full custom design. Semi-custom design means you already use something that has been designed and verified and all that, something which is already available, a block which is already available, and you reuse it. Okay, so you're not designing from scratch, you use things which are already available, something that has already been designed. Okay, let me give you an example of a semi-custom design where you don't design from scratch. Many of you may be familiar with 4:1 mux, right? 4 input lines, 1 output line here, 2 select lines here, and based on what you apply here, you can connect any of these input lines to the output lines here, right? So you can use a 4:1 mux, and you know that I can apply these 2 inputs A and B here, A and B to the inputs here, and depending on the values of A and B, I can put here C, C bar, or whatever, 1, 0, and thereby realize my function, right? So mux is a very well-defined entity. I may already have, since it's so well-defined and, so common, I already have a layout and everything available with me. A fully designed block is available, right? And what you do is, all that you need to do is, your inputs, wherever these inputs are coming from, all you'll have to do is connect them here, and the other input connect here, and the output here, and your design is ready, right? So very quickly, you've designed an IC which performs this particular function. What are the problems? And what are the advantages? Problems are, well, if I go into your mux, well, you may find, this is just a gate netlist description of a mux here. You may find within the mux you have all these 3 input AND gates, and you have an OR gate here and inverters and all that. That's what is there within the mux here, right? And so it has, for this particular problem, it has a lot many gates than are necessary, right? And obviously then is complex and it would occupy more area, right? So it's not an optimal design. It's very convenient. You take a mux and apply the inputs and your design is ready. But it's a non-optimal circuit in terms of, especially in terms of area. Not only that, if I look at the delay, well, the delay, it has to go through a 3-input gate and then another 4-input gate and all that. The delay may also be large. It may satisfy your constraint, I don't know, but the delay may in general will be large here. All right, so what is the advantage of this? The advantage is the design cost is very, very low. I mean, design cost is trivial here. You can do it in half an hour. The whole design, you can route the inputs and all that, and your design is ready. What is the drawback that you get? The drawback is that the area is large. The area is large, and therefore it will cost you a little bit more. If the area is large, then when you make all these ICs on a wafer, you'll get lesser number of ICs, and the cost will be high, right? But the cost of the final IC that you sell is not the cost of producing the IC, but is also there's a design cost involved. When you design something, you have to hire people to design that, right? You have to pay their salaries. And you have to use the CAD tools. As I said, all these designs are done with CAD tools. The CAD tools are expensive. There's a license fee associated with the CAD tool. They're very, very expensive. The CAD tools are $1 million tools. So when you use a tool for a certain amount of time, you're incurring a cost. So there's a design cost also. So it may happen, we'll have to work out, it may happen that even though this design occupies more area, and therefore the production cost of the IC may be high, but the design cost is very low. And so overall cost may turn out to be better, right? So usually you have alternatives like that. You have alternatives of semi-custom design, that you don't design things from scratch. You use a block which is already available and you use it for your application, okay? So that's an example of a semi-custom design. But what we are interested in, let's say we want to design the minimal area with the best delay, all that, we want to do a full custom design, okay? So our design will consist of series of steps. We can't jump from a logical expression to a layout in one step, okay? So we'll have a series of steps here. And in each step, in general, a series of synthesis steps. What you're doing is you're transforming each step is basically a behavioral representation into a structural representation. All right. For example, in the first step, what I would be doing is taking my logical expression, and this is a behavioral representation. It tells you how my circuit should behave. My circuit should behave according to this logical expression. So I have a behavioral expression. And this expression I have to translate in the first step, into a gate netlist, a structure. It shows you I have a NAND gate, another NAND gate, and an inverter. So it's a structure that we are looking for. So each synthesis step is a transformation of some behavior that is given, and you transform it into a structure. A structure which is an interconnection of elements here. Okay? So we have to do this. Similarly, if I take one element here, an inverter, and inverter is also a behavioral expression. It says in inverter, this should be Y. Inverter is Y equal to X bar. So it's a behavioral expression. And in the next step, what I'll have to do is each one of these gates, I'll have to transform it into a structure again. And this is a structure where it's now composed of transistors. Now, even in the next step, I'll have to take the transistors and convert them into actual layout where the elements are N plus diffusion, polysilicon, and metal layers and things like that. So it's a structure made up of those physical layers that are there. So every step of the design is involving a conversion of some behavioral representation into a structural representation. So let's look at the first step here. So I want to go from here to the layout. So first step is what we call as logic synthesis. Logic synthesis, which is basically converting a Boolean expression into a gate netlist, involves two steps: minimization, and the second step that we call is technology mapping. Minimization, all of you are familiar with. I'll take my expression, this expression that you see here, ABC and all that. I'm looking for minimizing the complexity of the Boolean expression. And K-map is one technique where we go ahead and do that through the K-map, and we obtain that original expression becomes simply AB plus C here. And why are we minimizing? Why are we simplifying? What is the reason we are simplifying the expression? Remember, our eventual goal is the minimal area. Because the goal is minimum area, and I know that if I take my expression and minimize the expression, eventually that minimized expression would take less number of gates. Less number of gates means lesser area. So eventual my goal is area, all right? And that's why I'm minimizing this expression here. Now, two problems. K-map, all of you are familiar with. You've used it many times. I think in second year, you probably minimize expressions consisting of 4 variables. Not more than that, 4, right? Now, 4 is very, very simple, right? We are talking about designing transistors with 100,000 gates and a million gates here. So, and I was telling you in the last lecture that if you look at the whole digital design, it's been continuously increasing in complexity. So, imagine maybe long back, K-map may have been okay for minimization. But let's say you have to minimize an 8-input, 8-variable circuit, 8-variable expression. What's going to happen? 8 variables, I give you 8 variables, long expression, and you have to minimize it. Well, even if you can do something similar to a K-map, you'll realize that even with a 4 or a 5 or a 6-input expression, the minimization becomes very difficult. Not only that, I'm sure we give you even 4-input problems we give you in exams, and we find that not everybody is able to arrive at the most optimum solution. Not only that, we find people make mistakes also, even with 4 input. So imagine if I have 6 or an 8-input expression, you won't be able to minimize it at all. Even if you attempt it and all of that, your final expression is not going to be optimal, and it's quite likely you'll make errors. So what do we do? You realize minimization is an important step. What do I do? You can't minimize it, so who's going to minimize it for you? Well, manual minimization is tedious, suboptimal, error-prone. A CAT tool is required. I have to bring in a CAT tool. I have to write an algorithm for minimizing it, and I have to give that expression to the CAT tool, and the CAT tool will minimize. And it's not going to make errors, right? And it's the quality of minimization that it will do will be much better than what you can do, right? Especially if I have 8 variables and 10 variables and all that, you just cannot match. A CAT tool is essential to my design process. Okay? If you want to take a Boolean expression and minimize it, there's no alternative but to use a CAT tool. Now, if we are trying to understand, so CAT tool is available. There are companies which will give you. There's a company called Synopsys. It has a very nice CAT tool. It will give it to you. You feed in the Boolean expression, nicely minimize it for you, right? So the tool is available. Of course, you should learn how to use that particular tool. But it's also important to know what is the algorithm behind that particular tool. How does that particular tool do the minimization? As engineers, we don't want to use things simply as a black box. Feed in and get the output, right? We want to understand how it does it. And if you understand something better, you can use it in a better fashion. So as part of digital design, we don't have too much time. We'll also look at, so if I have a tool which does the minimization, we would like to understand how does it do the minimization? What may be the algorithm behind it, okay? And so what we realize is that pretty soon, 2 input and 3 input, you can do it manually. Pretty soon, you'll have to do it using a CAT tool, the minimization step. The second step is technology mapping. What do I mean by that? Well, we have to map the minimized expression onto a network of gates available in the chosen technology. So the design has to be done with a particular technology. You may be using a bipolar technology. You may be using a BiCMOS, both bipolar and MOS. Or you may be using a CMOS, or you may be using a gallium arsenide-based technology. So there are various technologies that are available. For us in this particular course, we'll be using CMOS technology here. So what we have is in a particular technology, there's a particular kind of gates that are available. And so we have to take this expression and map it. Well, I can't simply do the following. AB plus C, so I can't do AB here and OR. Why? I can't do simply like this, because if I take CMOS technology, AND gate is not an elementary gate. AND gate is not an elementary gate, OR gate is not an elementary gate. You make an AND gate by combining a NAND gate and an inverter. You make an OR gate by combining a NOR gate and an inverter. In some other technology, it may be an elementary gate, okay? So what we have to do, elementary gates in CMOS technology, as you will see, are NAND. Of course, you can have 2 input, 3 input, 4 input NAND, multiple inputs, NOR, NOT, and things like that here. So if I want to map it into a network of gates, even for this very simple example, you know, if I just sit down, I can come up with this 5, 6 possibilities. Possibility 1, 2, 3, 4, 5. A very simple example, I can come up with these possibilities that are there. As I said, for every design step, you'll have to generate a set of alternatives. It's not that, well, first thought comes into my mind, do this, and just go ahead and take this and implement it. That's not an optimum way. You have to generate alternatives and then evaluate them and see, right? So in this case, I've generated 5 alternatives, 5 possibilities that are there. Now the issue is, how do I select? Remember, what is my selection? All of them perform the same function. They will do A, B plus C. All of them do that. But how do they differ? They differ in terms of area. They will differ in terms of delay. And in our case, these are the 2 main things, area and delay. They may differ in terms of power. Sometimes it's very easy for you to straight away eliminate some. You know, if I look at these 4, it's very easy to see that the minimal area is likely to be the first one, and the minimum delay is also likely to be the first one. It's the simplest one out of these 4, right? All of them otherwise use more components, and if I look at a path from input to output, the paths are also longer in the other case here. So the paths are longer, and therefore the delays are also likely to be longer. Yes, so it's very easy to eliminate out of these 4 and say this is the best one. Many times it is not. As you know, so the whole issue is, suppose this whole thing were not 3 input but 7, 8 inputs, and the netlist would have been huge. How do you decide which one is the optimal? Okay, even amongst, if you look at 1 and 3, 1 and 5, it's not obvious which one is better. Note that 1 involves 2 NAND gates and an inverter. The second one, in CMOS, you can make a single gate, which is AB plus C. A 3 input gate you can make, which has this property, AB plus C bar. And then you can add an inverter, and then you can get AB plus C. So that possibility is also there, a 3 input gate and an inverter, versus 2 input gates and an inverter. It's not obvious which one is better, which one will give me lesser area. Because note that at this stage, what do I have? This is just symbol, right? I mean, I don't have an area here. It's just a symbol, a NAND gate symbol or a 3 gate symbol. All I have is symbols. I know that NAND gate is probably composed of so many transistors and all that I can count, but area will become available only when you do the layout. Once you actually do the layout, you know how much area a particular entity occupies. This is too early a stage to comment on clearly saying this is going to have this much area. I don't have that particular estimate at this stage. All I can say is, well, comparing this is likely to have lesser area. All right. So various alternatives differ in terms of delay and area, and in general, it may be difficult to estimate these values at this stage. So what do? Let's in this case it's straightforward, but let's say 1, 2, 3, 4, 5 is not very clear. Especially between 1 and 5, it's not very clear which one is better. What do? What do? I have 2 now live alternatives, 1 and 5. And it's not clear to me which one will have the minimal area and which one will have the minimum delay. What do I do? Take both of them to the next stage? Would you want to do that? Take both of them to the next stage and then take them both all the way to the layout, then compare the 2 and they say, yes, this one is better. Right? Now, this is a very simple example where you have 2 alternatives between which you cannot distinguish. What if you have a lot more alternatives and you can't distinguish? You take all of them to the layout, all of them you make, 20 chips, and now compare which one is better, and they say, yes, this is the one. You can imagine what will happen, how much cost will be involved in the design, how much time it will take to do the design. It's not possible to do that. You have to take a decision at this stage. But if you have to take a decision, remember you're taking a decision in the face of uncertainty. You don't know how much area and all that. And if it's uncertain, it may happen, let's say you make a choice between this, and your area and delay constraints are very, very tight. So you make a choice between this, you carry it all the way to the layout, and then see, well, it fails. You're fine. You may have to go back and iterate again. Okay, so iteration is it's an inherent part of the design process because you're taking decisions in the face of incomplete information. You don't have all the information at this particular stage to choose a particular alternative. And if you don't have all the information, you can always make mistakes. And that mistake may have to be corrected and you may have to come back. Okay. Also, remember, I said it seems very trivial, right? Let's say I have the delay of each particular gate available to me. The delay of this gate and this gate and this gate and all that. All the delays, let's say all the gates have been made earlier, and I have a library of gates and I have delay values available too for all of them. Do you think I can accurately estimate the delay of this whole thing? If I have a delay of a gate available to me, NAND gate delay is 2 nanoseconds. Or 2 picos, or whatever, 2 nanoseconds, let's say. This is also 2 nanoseconds. Inverter delay is 1 nanosecond. What is the worst case delay? 2 plus 2, 4, right? You think that's the correct estimate of delay? 4 nanoseconds? It's not. Why? Because the wires interconnects, right, between two gates. The wires have capacitances associated with them. When you have to charge and discharge the capacitances, and that they also cause a delay. You have no idea about what is the length of the wire connecting between here and here. This is just a diagram on paper, right? How long you can make this wire as long as you want, right? Or as you have no idea about the interconnect, right? So delay, you don't have an idea precise. Okay, what delay will this particular circuit give me? Even if you know the gate of an individual NAND gate. Because the wires are not available to you. The wire delays are not available to you. Also, let's discount that particular problem. Let's say I have a schematic which is here. And let's remove the wire delay problem for a bit. I know the delays of each one of these gates. How do I check whether my circuit will work with that delay constraint? What would be my, let's take this circuit for example. Right, so here's the circuit. And in this circuit, the delay should be less than whatever 10 nanoseconds. How do I find whether this circuit meets the delay constraint or not? I know the delay of each gate. For the time moment, let's forget about the wire delay. How do I find it out? Whether this circuit meets my delay constraint or not, 10 nanoseconds. How do I find? What would be the method that you would follow? The circuit is given to you. You want to find out whether it meets the delay constraint or not. What method will you follow? Right? So what you would try to find out is, what is the worst case delay in my circuit, right? So you want to find which translates into, you want to find out the longest path in the circuit. The longest path could be, I don't know, this, maybe this, or this one, or whichever one. You want to find the longest path. And once you find the longest path, you add up the delays of each element on that particular path. So you calculate so what you're trying to do is find the critical path. And then add up all the delays on the critical path and check whether the delay is less than your constraint or not. If it's less, then it's fine, it's okay. How do you find the critical path? Well, here the gate netlist is given and you can look at it, right? And you can trace the path. But what if your netlist is here? Just a little bit more complicated than that. Can you find the critical path? And then I make it more complex. How do you find the critical path? How do you find it? I have a huge network of gates. I have, 10,000 gates. How do you find the critical path in the 10,000 gates? You can't use, well, I'll look at it and then trace it, right? You can't do that. So how do you find the critical path? Well, that's where you'll see every step of the design, you'll require a CAD tool. You can't do it. You can't do the design without a CAD tool. So there is a very nice CAD tool called static timing analysis. Tool is there. So what it does is it identifies the critical path and a number of other paths, will calculate all the delays along that and tell you whether the delay constraints are satisfied or not. You need that particular tool. See, it's trivial to do very, very small designs like this here on paper and be very happy with it. But that's not what digital design is about. Digital design is about doing complicated design. And you have to go ahead and use tools to carry out your design. So static timing analysis is one tool. And again, what we would like to do is understand what does this tool really do? How does it figure out the longest path? What is the algorithm? How does it work? Okay. So you realize the need for this particular one. Okay. So we said that this is, you can't take each one of those possibilities and go to the next stage. You have to take a decision and you may have to reverse those particular decisions here. Now, so you've done synthesis. Let's say you've done the synthesis by taking a logical expression, minimizing it, and technology mapping it, and you arrive at this one. All right? Your design step, the logic design step is not complete. You have to do verification. Because there are always errors. You have to do verification. And there are two kinds of verification that you need to do. One is what we call as horizontal verification. In general, all verifications are, at every design step, you can talk about two kinds of verification. Horizontal and vertical. What do I mean by that? Horizontal verification, let's say I have a gate netlist like this. I check whether my circuit complies with certain limitations. There are limitations on fan in, how many inputs you can have, limitations on fan out. That in my, while I'm synthesizing my circuit, I didn't leave any input open. There are things like that, where I look at my netlist and there are certain checks that I perform on it, that it meets all those, things like fan in, fan out, floating inputs and all that. So that's what we call as horizontal check. Every design will have certain rules. If you violate those rules, the design is not going to work. If you leave an input open, that input may get stuck at 1 or a 0 or whatever, it's not going to work. Okay, so that's what we call as horizontal verification. But more important is a verification which is vertical. Vertical in the sense that look at what we did. We took a Boolean expression, right? And we transformed it into a netlist. We went from here to here, a gate netlist. And this is what is called as the logic synthesis. Now, as you go from a Boolean expression to a gate netlist, there are possibilities of errors. There are possibilities of errors that you didn't correctly translate the Boolean expression into a gate netlist. Especially as the design becomes more complex, there are chances of error. And remember, when you're talking in terms of error, it's best to catch errors as early as possible. If you let this error pass to the next design stage, it's going to become even more costly and more difficult to detect. So catch errors as soon as possible. That's the general rule. So we have carried out a design, and I have to check whether this particular design indeed does, what this expression is supposed to do. So what do? I take my gate netlist, and this is a behavior, a certain behavior that I expect, and I extract a behavior from here. What do? Basically logic simulation. I apply 0, 0, 0. I expect a certain value y here. And when I put 0, 0, 0, I expect a certain value y here, and I see whether the two match or not. Right? So that's what I'm doing. I'm doing a logic simulation on my circuit. I'm doing logic simulation and verifying the results from my gate netlist with the results that I obtained from my Boolean expression. And if it, after doing this, if it matches, then I know that this is a faithful translation of this particular step here. I can now say, well, let me go to the next step here. So every design step involves a synthesis step where you synthesize a circuit, and then it involves a verification. And verification has this, we call it vertical verification because you're comparing from a gate netlist against the specification. The previous one, we called it a horizontal verification because we were not comparing with this thing here. We were just looking at the netlist itself and saying whether it satisfies certain properties or not. Okay? So we have to do that. So there, yeah, again, I should have said, even simulation, well, you can go ahead and put 101 and do all that. You can't do it manually. So that's a whole area. How do you verify? In fact, designing may be easy. Synthesizing may be easy. You can take some expression and synthesize and give it. Verification is more difficult. Right? So it's a challenge. So we have tools and algorithms for automating the verification process. Okay? So anyway, so we see that you require a CAD tool for logic simulator is required. And as he rightly pointed out, I cannot apply all possible inputs here and compare the two things here. I have to look for other ways of verifying. Okay, so this is a general, as I said, verification. When you go from a design step level n to level n+1, you carry out a synthesis step, and then you have to compare the two. So you extract behavior and you look at the desired behavior and you see whether the two match or not. And only when the verification is complete do you go to the next level of the design. Okay? All right, our next phase. So we've obtained the gate net list. So from gate net list, now in the next step, what do we want to do? From gate net list, I want to go towards the transistor schematic, to the transistor level. And we do circuit synthesis. So this was, we were calling it logic synthesis. And now let's say transistor schematic synthesis or transistor level synthesis here. And again, I have to verify also. After I do that, I have to verify. Okay. So how do I do that? What are the things involved? So I have a gate netlist and I have to get to a transistor schematic. So one of the things that we have to do is choose a particular circuit style. There are different ways in which you can implement a gate. Okay. For example, a NAND gate that you're aware of, I can implement it using what we call as a static CMOS or a dynamic CMOS circuit. The static one, I can do it using fully complementary or pseudo NMOS. Let me give you an example. Fully complementary NOR gate is here. And a pseudo NMOS NOR gate is here. All right, so I have to make a choice. How do I implement it? Each one of them, if you look at this and this, you can obviously see the areas are going to be different. This has 6 transistors, 3 PMOS and 3 NMOS. This has only 1 PMOS and 3 NMOS. So there's a choice. It may occupy less area. But this one may consume more power as compared to this one. The delay may be smaller here. So each one comes with its own characteristics in terms of area, in terms of delay, in terms of power. So looking at the problem at your side, would you use a static or a dynamic? Within static, which one will you use? You have to make a choice. And the choices are always with the idea of area, delay, power. These are the things that, you make a choice. Because each one of them you can use to satisfy the, make the gates that you want. So as far as functionality is concerned, each one of them will give you the functionality. A, B plus C, each one will do it. They'll differ only in terms of area, delay, and power. And you have to make a choice. And it's not easy to make a choice again. Because remember, area, delay, and power, they'll all be available at the end of the design. After the design is over, the exact values of area, delay, and power become available only then. At any previous stage, you can only do an estimation, and estimations can go wrong also. Okay? So anyway, so this is what we have to do. So we have to become familiar in this particular course with CMOS, different ways of designing CMOS gates, we'll see, and look at their properties and choose one over the other, depending on what you're looking for here. So, for example, let's say this one. This is the gate netlist that we are talking about, and I choose a fully complementary. Fully complementary means same number of NMOS, same PMOS. The PMOS side is exactly complementary to the NMOS side. So it's a fully complementary here. So I choose a fully complementary one. So I have a NAND gate that you see here. I have an inverter, and I have a NAND gate, another NAND gate, and all that here. Now, the problem, so the first problem was choosing which circuit style do I use. The second problem is, what size of the transistors do I use? This is a freedom that a designer has. You use the size of the transistor 2 by 1 means the width of the transistor is 2 micron, the length is 1 micron. Do I use 4 micron or 1 micron? So a very important part of the design process is the sizing. How do you size the transistors? Do you use the minimum size or you use higher size? How do you do that? Well, again, the whole problem is to meet delay specs and the area specs. You don't want to unnecessarily use a large transistor when it's not required here. So again, in this case, we may see that if I put a somewhere here, and I may have to look at the path, the critical path, how it travels, and accordingly size the transistors larger or smaller that is there here. So note that as the circuit becomes bigger, your transistor schematic is also going to, for each gate, in this case, you have 4 transistors. So if you're talking about 100 gate transistor, it will become 400, roughly 400 transistor schematic. How do you size it? The problem just gets out of control. You can't size a 400 transistor or a 1000 transistor circuit. Again, the whole problem is one of complexity, and sizing also has to be done under uncertainty, because sizing has to meet delay and area. Again, at this stage also, I don't have any information about my interconnects and all that. Again, a circuit simulator is required. At this stage, a circuit simulator will be required to verify performance and functionality. You may design a schematic. You may incorrectly, transform this into the schematic, make errors. So you have to verify that this indeed does what it's supposed to do, and also for performance as well. Okay, same more complicated one. Imagine that I take this particular gate netlist, I convert it into a transistor schematic, and then I have to size. I have to find the optimum size of the transistors. Okay, so circuit dependent, depending on the circuit, custom sizing of transistor becomes almost impossible. Very difficult. That depending on the circuit, I decide a transistor here and a transistor here, and that would be the optimal solution. But I can't do it. The problem is so complex that I can't do it. Okay. So anyway, let's go to the next stage. We're running out of time. So let's say we have done the circuit synthesis, and we have verified also, and we've obtained a transistor schematic. In the last stage, as I said, design is only complete when you have a complete plan for its fabrication. So you have to do the layout. Okay, so we have to do what is called layout synthesis, and once you get a layout, again you have to verify that the layout is indeed has been correctly done, so it matches with the transistor schematic. So we don't know, as we have not gone and looked at MOS transistors and the way it's fabricated and all that, but even effectively what we need to do is, if I look at an inverter, I have to convert it into a sort of a drawing like this here. Okay, so this is where, for example, I have to tell, this is where my N plus region is. This is where my gate is. The red region is the gate, polysilicon. This is where the N plus is. These are the contacts that are there. This is where I'm making a PMOS here. The PMOS and the NMOSs are connected together. This is where I'm going to have VDD. This is where I'm going to have ground and all that. So this is where now I'm talking about how the transistor will be actually fabricated. If you make the layout, let's say the layout is ready. The layout is effectively a drawing showing various layers that are there. This drawing or the layout can be digitized. It's available in the form of a file. And once you have that layout file, you can send it to a foundry. The foundry can take this information and fabricate the IC for you. Okay, so the design from a designer's point of view is complete after you get the layout. Once you have the layout, you can send the layout nowadays over email. You can send it and get it fabricated. Okay, so that's where the design ends. Now, layout is obviously, you can see here, each transistor, NMOS and PMOS, it takes time to fabricate here. Now, there are two kinds of checks that we have to do. Remember, every verification step is two: horizontal verification and vertical verification. Horizontal means I check for design rules. Every, when you make a N plus region, there are rules that it cannot be less than 3 micron or 2 micron or whatever. There are rules for every width and lengths and things like that. So you have to check all those rules. We call that DRC, design rule checker. Obviously, it can't be manually done, so we have a tool which does the DRC, design rule check. And then we have a check called layout versus schematic check. Remember, we said that you have a design step. So what we do is, from the layout, once you do the layout, from the layout, we extract the schematic back. By looking at the layout, we know that there is a transistor NMOS, so we put an NMOS here. We know there's a PMOS, so we put a PMOS here. We see that there's an interconnection, we interconnect here. So we extract a schematic. So from the layout, a new schematic is extracted. And this schematic is checked with the original transistor schematic. So that's what we call as layout versus schematic check. Once it passes that, then you know that your layout has been faithfully done. That layout will actually do what it's supposed to do. All right. The other thing that happens is, once you extract the schematic here, Along with that, now you have the exact lengths of wires and everything. You know that this PMOS is connected with the wire NMOS, and the wire length is so much. So you have all the parasitics available to you. So when you extract the schematic here, along with that, you get all the parasitics, all the wire lengths, everything becomes available here. Now, if you do a simulation, the simulation will give you accurate values of delay. So at this stage, you know that your inverter occupies so much area. At this stage, you know how much delay is available. So your final chip performance is available at the end of the layout phase, right? And at the end of the layout phase, if your luck is not right, you made bad decisions, you find you don't meet the area constraints. You need to go back to an earlier stage and fix it, okay? So, for example, the layout for our simple cases, 2 NAND gates and an inverter. So we have a NAND gate here, we have a NAND gate here, we have an inverter here, and the two are connected together. Now remember, you may have a layout for a NAND gate, you have a layout for this and layout for this. The problem at this stage is what? The problem at this stage is, even if you have the layout of each gates done beforehand, the problem at this stage becomes, where are you going to place each NAND gate? And how are you going to route? So the problem at the layout stage is, the main problem is what we call as placement and routing. Where are you going to place each transistor, or where are you going to place each gate, and how will you route? Now again, as the problem becomes large in complexity, what will you do? A placement and routing tool is required, which will do the placement for you, which will do the routing for you, all right? So you see the role of CAD tools right from the start to the end. Without that, no modern design. So for a very simple design here, this is what we have done. Boolean expression, we've done logic synthesis, arrived at gate netlist, done logic verification to verify this particular step. You do circuit synthesis to arrive at transistor schematic, again do circuit verification. You do layout synthesis, you obtain mask layout, again you do verification. Everything is right, you obtain the final plan for fabrication, and your design is complete, okay? All right. As the circuit becomes more complex, you have to add more design steps. You don't start at Boolean expression. You have to start at a higher level. Okay, so we will have something on top, more design steps that are there, okay? All right, this is the last one. If I draw a line here, all this is called, this part that you see here is called front-end design. And all this part here is called physical design, and it also goes by the name back-end design.